Okay, thanks. So let me start by thanking Anindya for organizing this. Um, I have prepared the talk with students in mind and also Chetan in mind, but Chetan is not coming to the seminar. So the title of my talk is Small Black Holes in String Theory, Informal Discussion. I will present various aspects of this story and then present our recent results on this subject. So I have been working on this for about 2 years now. So we have some interesting results which I will highlight towards the end. Okay, so arguably one of the biggest successes of string theory is statistical mechanical explanation of the entropy of a class of supersymmetric black holes. What one does is that one considers supersymmetric compactification of string theory, typically on torus or some K3 manifold or something of that type. Then at weak couplings, the microstates are bound states of strings and branes, and for these states one can compute an appropriate supersymmetric index, and this was done by Strominger and Waffa and thousands of papers after that. Having said this, we know that black holes in string theory is a very big and confusing subject. There are many aspects of this story. So one aspect is this small black holes. In this talk I will focus on the simplest setup which has been discussed from the 90s. This is the highly excited fundamental string. So this is a problem on which many great minds of our times have worked. Witten, Maldecenas, and almost anybody you can think of thinking about black hole has written a paper on this topic. Unfortunately, the subject remains ever more confusing. There are many varied viewpoints, and it is not clear what is the key. Even today, there was a paper on this this subject. So, in my recent papers, we have addressed a few technical points on this subject, and the idea is to present the context and some of the results. So actually, in February, I gave a much more technical talk here. So this is a very different version of similar subject, but different talk completely. Okay, so consider BPS states in string theory carrying two independent charges. These states have played very important role in understanding of black holes. So one can think of these states as take a heterotic theory on S1 times some T4, let's say. And on this S1, you wind string W number of times, and you put a lot of excitations on this string, n excitations. So these are the two charges on the string, n and W. So this state is supersymmetric. These are known as such a configuration is supersymmetric, and the states are known as the Davolkar-Harvey states. From the counting of these states, we know that the degeneracy of these states grows as 4 pi square root nw, exponential 4 pi square root nw for large n and w. In fact, the answer is known for all values of n and w. I'm showing the answer only for large values of n and w. W is the winding, so how many times this string is wound around on this S1, and n is the number of momentum excitation it carries. So the question that has bothered many people is, can this degeneracy be reproduced by computing the Bekenstein-Hawking entropy of a BPS black hole carrying the same charges? The question turns out to be surprisingly difficult, and it has attracted attention of everyone who has thought about black holes in string theory. A straightforward analysis shows that the supergravity limit, one can simply construct such solutions. They are not very difficult to construct. But as you take the BPS limit, one finds that such a black hole has zero area, and hence it is singular. Now, this has been suggested by many people that upon taking into account the effect of higher derivative corrections, the black hole could develop a finite area event horizon, and that way one can hope to reproduce that answer. Okay, so this is the picture that is taught. If you go to a school in string theory where people are teaching black holes, this is what they will teach you. That this happens, and I mean, you first assume that higher derivative corrections correct the solution in such a way such that the finite entropy area appears. If this happens, then a scaling argument can be used to show that the entropy of such a black hole must be of the form some constant times square root nw, where this numerical constant c cannot be fixed by this scaling argument. This is left undetermined. Later in 4 dimensions, Davolkar in 2004 computed this C in a higher derivative n equal to 2 supergravity, and showed that the answer for C is 4 pi, in precise agreement with the microscopic result. Okay, so this is regarded as one of the biggest success in this subject, but this is a very clean way of saying it. There are many issues here. Okay, so there are many confusions, so I highlight some of these big confusions. So first big confusion in my opinion is how to understand this Dabholkar-Harvey states in supergravity. So there is a big debate between Mathur and Sen on this topic. Sen has argued that since these Dabholkar-Harvey states are singular in supergravity, they should not be thought of as microstates. One should compute the index and just compare that index with the index of the black hole. On the other hand, Mathur has argued that these are states which are singular, but the singularities are allowed sources in string theory. Fundamental string is an allowed source in string theory, so one should consider this as a possible microstate. And there has been counting done for this, and Chetan has written papers on this, for example. And indeed, I mean, it's difficult to decide one way or the other. Both arguments are good, and Sen's argument also seems to give good answers. Mathur's argument also seems to good answer. No. You can ask separately, or you can ask now. I am happy to. The stress tensor is okay, but his objection is the source itself, the fundamental string itself is a source which is a singular source in string theory. Like supergravity solution itself is singular at the location of the location where the string is there. And hence he says that we don't consider electron as a valid source in quantum field theory. I mean, electron is replaced by a field, and similarly one should replace maybe fundamental string by a field, and that will resolve that. Then this singularity issue will not be there. But on the other hand, Mathur has said that since we are doing string theory, fundamental strings are allowed objects, so fundamental strings can source whatever they are sourcing. And now whichever profiles you consider for fundamental string, you count them how many such states are there, and that gives the entropy of the two charge black hole. Okay, so this is one big confusion. There is no clear. Yeah.
What are we counting to get the black hole entropy? What would the answer?
So I will come to that. Yeah. So this is actually the third point. So what are we counting on the microscopic side? This is very closely related to Anindya's question. What are we counting on the microscopic side? Actually, in this case, one can count both index and degeneracy. There is no difference. Microscopic side is very easy. But the question is, what are we counting on the macroscopic side? And in particular, what is the meaning of the index on the gravity side? This is the main question. And this is what we answer in this first paper that I wrote. Actually, there is another big confusion with this Dabholkar's calculation, which I have not listed in a thing. So it turns out that the coefficient C turns out to be correct. But if you look at one of the moduli, which is the size of the so this is ADS2 times S2, but there are also other 6 directions. One of the S1s shrinks to 0 size when one does this Dabholkar 2004 calculation. And that is also not clear how to resolve this issue. So there are many issues. That is also another issue. Dabholkar et al. Calculations is only restricted to only F terms, and the D terms are not included, so that is another issue. It's not clear. Yeah, so I will mention this. Yeah. So this is one of the. So how reliable is Dabholkar 2004 calculation? So first question is the near horizon structure justified? So a big assumption is that ADS2 times S2 is there. It's not clear whether that statement is correct or not. Is interpolation to flat space possible? Ashok has written papers saying that interpolation is not monotonic. Whereas all the black holes that we know, short shell black hole or Kerr black hole, whatever, the interpolation from flat space to near horizon region is monotonic. But in this case, it is not monotonic. And related to Justin's point, can we show that 6 and higher derivative terms do not contribute to the entropy? Okay, so today there was a paper about this. So it's not fully clear if in n equal to 4 theories, ADS2 times S2 can be fully supersymmetric. Can ADS2 times S2 can have 16Q supersymmetry? This issue is also not clear. Okay. On the microscopic side, things are more or less dimension independent. You do this computation on S1 times T4 or S1 times T2 or whatever, even if you don't have any teeth, the answer is always the same. But on the gravity side, there is a very strong dimensional dependence. The nature of the singularity of a small black hole is dependent on the dimension. So this is also a big confusion. Oh. No. So the issue is that if you take n equal to 2 supergravity, in n equal to 2 supergravity, ADS2 times S2 is maximally supersymmetric solution. So it has 8 supersymmetries. But if you take n equal to 4 theory, then it has 16 supersymmetries, and it is not clear whether ADS2 times S2 has 16 supersymmetries or not. So 8 supersymmetries it has, certainly by embedding, but I don't think it has 16 supersymmetries, but okay, so this is the first paper we wrote on this subject. So we explain how to compute the index for small black holes on the gravity side, and we use this scaling argument by Ashok, and we show that the index also scales in this way with the similar numerical constant which we cannot fix. And we explain how the dimension independence works on the gravity side. So on the black hole side, there was this problem that singularity of the black hole is very strongly dimensional dependent. But here we explain how the index is not dimensionally. How the index, there is a dimension independence for the calculation of the index. Okay, so this is the outline. I have already finished the introduction. I will say these sections are very small, then I will say a few things about. So let me start with sense argument. So scaling argument. So the scaling, I mean, I am not going into all the details. I will just go you roughly what the argument is. So consider a black hole in two derivative theory in d dimensions that carries number of electric charges and angular momentum and mass. So the Bekenstein-Hawking entropy for such a black hole will be some function of m, q, and j. Now, since it's a two derivative action, one can see that if you scale the metric by lambda square and scale the gauge fields by lambda, then the action scales with definite power of lambda. So the action has a scaling symmetry under such scaling. In fact, the scaling symmetry is lambda to the d minus 2. So this scaling property, because action scales as the entropy, so the scaling property tells us that in d dimensions, the function for the entropy should have this property, that if you scale the charges by lambda to the d minus 3, mass with lambda to the d minus 3, and j with lambda to the d minus 2, the entropy should scale with lambda to the d minus 2. Now, if you take the macroscopic limit, then we are supposed to take large lambda so that all these quantities are large, and then the entropy will scale as lambda to the d minus 2. And if you are confused about these factors, one can fix these factors from the scaling of the metric. Okay. Now, you see, so the scaling is lambda to the d minus 2. So in 4 dimensions, this is lambda square. But earlier I showed that for the two charge system, the entropy goes as n times w. So if you scale this with lambda, you will only get a factor of lambda. You will not get lambda square. So that's why the scaling argument does not work for the small black hole. It only works for large black holes. So this will be useful later. From the scalings that I wrote in the previous slides, one can see how the temperature, chemical potential, and the angular velocities will scale. So temperature scales with lambda, chemical potential for the charges scale like 1, and omega scales with lambda inverse. So this will be useful in a later part of the talk. So when we do gravitational path integral, we have to fix these chemical potentials. So in the gravitational path integral, beta, mu, omega will set the asymptotic boundary conditions and will be taken as independent variables. Okay, so now moving on. So the index, so what is an index? So index in the context of black hole counting is motivated in this way. So the computation of degeneracy is done by representing the black holes as some states in a brane system carrying the same charges as the black hole. Dynamics of the branes is understood at weak coupling, and this is the place where we will do the counting. The black hole description is valid, on the other hand, when the gravitational coupling is large and horizon size is large. Can we compare the two? And the answer is that we compare through this supersymmetric index. So supersymmetric index does not change as we vary the coupling constant. So we compute this at the weak coupling and compare it with the answer at the strong coupling. So consider a supersymmetric theory in d dimension, and what we define is this quantity. So trace is over all states with fixed charge q, and we are taking a trace of e to the minus beta h. So this is just the energy of the e to the minus beta Boltzmann factor, and then minus 1 to the f. This is f is the fermion number of the state. This is called the Witten index. The trace gets contribution only from supersymmetric states, because if the state is not supersymmetric, then acting by q on this, we will get a state with the same mass but different fermion number. So so when you calculate the trace, you will get the same mass but different fermion number. So when you trace over minus 1 to the f, the contributions will cancel. So only for BPS states you will get a non-zero contribution from this. A generic non-BPS state will break all supersymmetries and will not contribute to this index. So one can show that this index does not change as we change the parameters of the theory, in particular the string coupling. So one can compute this at low couplings and compare with the answer at the strong couplings. Okay, so on the microscopic side, one can compute the index for the brane system. This counts the number of BPS states with some weight. This weight is e to the minus beta m. And since only BPS states contribute, all BPS states have the same mass. So this is just a factor that comes out. And trace over q minus 1 to the f gives some number. And that number is what we are calling e to the SBPS. So e to the SBPS is the BPS entropy of a system defined through this Witten index. So mass factor simply comes out, and this is the definition of SBPS. Okay. So this is slightly different from the way we compute the entropy of BPS black holes, but in this talk, this is the way you can think of it. This is the entropy coming from the index or whatever. Okay. So to compare with the results for the black hole on the gravity side, one also needs to compute the index on the black hole side. And what one does, so this was pre-2018, what one does is that one argues that index and degeneracy are approximately equal. So one can compare the SPPS with the entropy of the black hole. So this has led to successful comparison, and it works in all cases. But this business is problematic for small black holes or for black holes with hair, because then there is some confusion about, for small black holes we do not, because the entropy is 0 in the two derivative theory, we do not know how to compute the index. So the problem is there, and for the black holes with hair, there is some confusion about whether we can compare the entropy with the index directly or not. Okay, so the question really then becomes, for small black holes, we know how to compute the index on the microscopic side. Can we compute this on the macroscopic side? Can we compute the index for the black hole directly? Okay. So this can be done. So this is done using gravitational path integral. So define Z as the path integral over all fields weighted by the action. So we do path integral over the metric weighted with the action, and with the following asymptotic boundary conditions. So we do this in the Euclidean signature. Euclidean time tau periodically identified with the period beta. The contribution is dominated by a saddle, and the saddle is Euclidean black hole with a temperature beta. And in that approximation, we can compute the log of Z S simply minus the action in the semi-classical gravity approximation. Yes, sir. Okay. So let's see how this works. So once we know the partition, so you see what is happening is that, so we are computing this gravitational path integral using saddle point approximation. So once we have computed this, we know what the value of z is in the semi-classical approximation. Now, Euclid, I will come to. I will come to the small black hole. I'm just doing the gravitational path, general discussion on gravitational path integral. Yeah. So once we know the partition function, so left-hand side is known using semi-classical saddle point approximation. We interpret this as trace over e to the minus beta h, and then using standard thermodynamic argument, we can compute the entropy of this system. And Gibbons and Hawking found that the entropy computed using this is simply a over 4 for the Euclidean Schwarzschild. Okay, so now we have to make it a bit more complicated. We have to add rotation to this subject. So consider, this was also done by Gibbons and Hawking, nothing new. So consider Euclidean gravity path integral in asymptotically flat spacetime with S1 times S2 asymptotic boundary. So S1 has a finite size where S2 has this infinite size growing to infinity as R goes to infinity. Now, because there is a S2, there is an identification on the phi circle. Phi goes to phi plus 2 pi. And now so now here one has to be careful. So indeed, there is a circle that shrinks to 0 size at the horizon of the black hole. But the circle that shrinks to 0 size is the orbit of the horizon generating killing vectors. So for the static black hole, the horizon generating is just partial t. But for a rotating black hole, the horizon generating killing vector is partial t plus omega del phi. So this is the vector that will shrink to 0 size as you go in the interior of the spacetime. So that changes the boundary conditions a little bit. So not only tau has to be identified with beta, but also phi has to be identified with beta omega, and one must do path integral over states which satisfy these periodicity conditions. Okay, this will take into, so this is what I was saying, that the specification of boundary conditions involve these chemical potentials, beta omega, and so on. Okay, so now getting towards Justin's question. And also the answering the question how to compute the index. So this is this great work by these authors. So what we do is that the Euclidean gravity path integral with the above boundary condition computes the grand canonical partition function, which is this quantity, e to the minus beta h plus beta omega j. So now the key idea these authors proposed is that in this you put beta omega equal to 2 pi I. If you put this, then e to the beta omega j factor becomes e to the 2 pi I j, and this can be interpreted as the minus 1 to the f, minus 1 to the fermion number. Now with these new boundary conditions, that is to say we are considering rotating black holes, and at the same time we are putting beta omega equal to 2 pi I. With these new boundary conditions, the gravitational path integral now computes the supersymmetric index. Is no longer computing the grand canonical partition function, but because of this business, it is now computing the supersymmetric index, which is what I showed in the earlier slide. Okay, so now specifically Z is now computing this quantity where we have set beta omega equal to 2 pi I. Okay, so now there is not fully clear understanding of this, but in all the examples that we know, at least in asymptotically flat spacetimes, when you put beta omega equal to 2 pi I, this forces h equal to mbps, and again this factor simply comes out, and what you get is e to the beta s times e to the minus beta m. So now this is where new understanding of black holes have arrived. So therefore, even by working with a finite temperature black hole in the saddle point approximation to compute the partition function using the semi-classical saddle point approximation, we can study the contribution to the supersymmetric index for black holes, which is what is on the right hand side of this.
So beta is an observable quantity, right?
Yeah.
And omega is also an observable.
Yeah, the boundary conditions are fixed using beta and omega.
Real black holes, beta omega cannot be.
Beta omega can never be 2 pi I. Yeah, for real black hole, beta is real, omega is real, but you do some analytic continuation or do something such that you force beta omega equal to 2 pi I. I will explain. Yeah, I will explain. Okay, so there are some subtleties about relating the left and the right hand side, but these subtleties are not there at the level that I am presenting in this talk. In the classical limit, the above statements are correct, but if you want to ask more detailed questions about one loop correction to this, then one has to worry about the choice of ensemble, but Ashok has written a paper on this topic also. Okay, so to answer Sanindya's question, I will go over this part and slowly come to examples. So even in the purely classical limit, this new understanding of how the finite temperature black holes relate to supersymmetric black holes is non-trivial. It leads to a relation between entropies of zero temperature and finite temperature black holes. Okay, so you have consider Kerr-Newman black hole. So Kerr-Newman black hole has finite temperature, it is rotating, it has some entropy. Now the prescription says you put beta omega equal to 2 pi I in this solution. In this example, it turns out that the Euclidean solution is perfectly smooth, and one can compute the entropy of the Euclidean solution. So this is this quantity, S non-BPS. And the prescription says that now you add to this 2 pi ij, which is also well defined for Kerr-Newman black hole. Kerr-Newman black hole is rotating. Only thing you have done is that beta omega is some complex number, so j turns out to some complex number such that 2 pi ij is real. I mean, j turns out to be purely imaginary such that 2 pi ij is real, and this gives the BPS entropy. So this is the way it works. Okay, so so this was in 2021 that this prescription came, but for 2-3 years nobody understood what is going on. Like there were no papers, and somehow things were not clear what is happening. The paper also very complicated, so it's very few people understood what is happening. So this relation led to conjectures that Euclidean finite temperature rotating black holes saturating the BPS bounds are supersymmetric. This conjecture is there already in the first paper on the subject, but it's just that the paper was so complicated that very few people understood really how to do this. So in 2 remarkable papers, Atira, Anupam, Chaudhary and Sen in 2003, they did very non-trivial tests on these ideas. So what they said is that now there is a proposal for computing the index on the gravity side. So let us compute logarithmic corrections to this index. So they computed the logarithmic corrections to 4-dimensional and 5-dimensional index, and they found that the answers are matching with the previous calculation which he did in 2004-2005. So that was very remarkable, and those papers actually led to a lot of understanding of what these people were saying and what these people were doing. So soon after these papers came out, I also understood the subject, what is happening. In my first papers on this topic, we wrote killing spinners for several examples. So this was done with Subbu in 2023. So this was in an attempt to understand this conjecture. So we took exactly Kerr-Newman black hole, analytically continued with beta omega equal to 2 pi I. So whatever metric we get, we found killing spinners for that metric. So, okay, in this case, you can do a Euclidean continuation and you can make it perfectly smooth Euclidean metrics. But in many cases, they are known to be complex metrics. By imaginary numbers there. In particular, for ADS5 black holes, it is not known how to make such metrics purely real. They always turn out to be some complex numbers are always there. But in some examples, you can do analytic continuation and make them perfectly real. It depends on dimensions. I mean, because too much richness is there. There are terms in the metric which are imaginary. Yeah. So in this example, everything can be made real, for example. Or 5-dimensional rotating black holes in asymptotically flat spacetimes, you can do analytic continuation and make them real. You see, the situation is like this. If you do, in the Kerr black hole, if you do t going to I tau, the metric has imaginary numbers. But you can also do a going to IB, then written in terms of tau and b, the metric will be real. So in some cases you can do this, in some cases you cannot do this. So in particular, in the 2 examples we looked at in this paper, it was possible to do this, but it is known that in ADS5 it is not possible to do this. And there are other examples known where it is not possible to do this. For black rings, for example, it is not possible. There is no analytic continuation one can do where the Euclidean sections are purely real. So. Signature, what do you mean? Like when you do Euclidean continuation, then everything will be plus, 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 plus. No, so then it's an interpretation. Then how do you interpret? Because there are imaginary numbers in that. Yeah. So actually the rules of the games are still not fully clear. Once you have a metric with imaginary numbers, what do you mean by smoothness of that metric? What should one check? So there is this K Kostanovich-Segal-Witten criteria, KSW criteria. Using this one can check a few things, but I don't think there is a full understanding of what all one should check. Okay, so this was the first project. Then in the second project, we explored the index of the small black hole, and this is where I will come to now. So to answer Justice's question, this is what we are doing. So to compute the index for small black hole in d dimensions, we need to look for a rotating black hole in d dimensions, and we need to put this beta omega equal to 2 pi I into that black hole. And then what we should be looking for is 2 charges. Yeah. So what we should be looking for is that some non-extremal solution whose S non-extreme or non-BPS, or whichever way you interpret this, this is non-zero. But when you add to this 2 pi ij, it becomes 0. This is the kind of solution we are looking for. So the question is, are such black holes known? Are they smooth? What if they are not smooth? What is the nature of the singularity, and so on? This is the questions these are the questions we answered in this paper. So now I will show some results. Okay. So for the small black holes, the answer to this question is that there are these Horowitz-Sen black holes. So these black holes are known, perhaps not very widely. In fact, Ashok had himself forgotten about them, even though he constructed. I will show you the email conversation in the next slide. And then I had to remind him that indeed such black holes are known. In fact, you only constructed such black holes many years ago. So, so these are, because we need to set beta omega equal to 2 pi I, we only need one rotation parameter. So, and exactly these solutions were constructed by these authors. So, so these are single rotation black holes with general charges. General charges in the sense in the duality orbit of the 2 charge black hole in heterotic supergravity compactified on a torus. So the charges are m, j, and electric charges in d dimensions, and the black hole has many, many scalars because heterotic theory compactified on t's have many crazy scalars. So I will spare you the details. Let me just say that they are not the most easy objects to work with. Similar black holes with multiple rotations are not well studied. There are a few papers which discuss these things, but a better discussion is required to understand what is happening with the yeah, it is. Yeah, so actually there is a confusion about this. So if you take a fundamental string and rotate it in this way, I mean, there are multiple confusions, but first of all, there is a diffeomorphism on the fundamental string, so one cannot really rotate them in simple way. One has to rotate them in a particular way, and then it's not clear whether it will become a black hole or it will become a black ring. So that depends on the scaling of the angular momentum. So if the angular momentum also scales with n times w, then Davolkar and Sen have argued that such objects become black rings. But if you don't do any scaling for j, then it is not fully understood how the system will be. But So in this case, if you only turn on one angular momentum, then such confusions are not there. I mean, they are fundamental strings rotating, but the angular momentum is not scaling as high as NW. So as far as I understand, I can be wrong on this, but these are black holes which have angular momentum and two charges. Yeah. So yeah, so there is this confusion about, because in higher dimensions you can have multiple rotations, and it is not clear what is the interpretation of these multiple rotations. So there are solutions known, but it's not fully clear how to use them, how to interpret them. It's not clear. Anyway, so this is the email conversation with Ashok. So Ashok is saying to me that all that it would require is to replace the starting curve solution by a Myers-Berry solution and apply the same solution generating technique that we applied for the curve black hole. But then I told him, thanks Ashok, but this is what you did with Gary Horowitz many years ago with one rotation. And he said, yeah, thanks Amitabh for reminding me of my paper with Gary. Long time ago somebody told me that if you start reading your own papers, then you are getting old. Okay. So once you understand that this is the black hole you have to work with, then life is simple. I mean, the difficult part was to identify that this is the paper one has to work with. But once you identify the correct black hole, then it's a few lines of calculation to check whether this plus this is giving 0 or not. So indeed this works out very nicely. Okay. So so this black hole, we argued that it was not, it has a singular horizon, it is not smooth. And here we are finding that this quantity is 0. So it cannot be that the rotating BPS metric is perfectly smooth everywhere. It turns out that in the Einstein frame, the metric is perfectly smooth. There is no singularity anywhere. Actually everywhere, everything is perfectly well defined. It's just that the string frame metric is not smooth, and dilaton, and the reason this happens is because the dilaton for this solution is not smooth. And the singularities of the dilaton is what is 26 is consistent with the expectation, yeah. But since, okay, so the point is that since the small black hole is not smooth, it cannot be that the saddle solution is also completely smooth. There should be something wrong with that solution. And indeed, what is wrong with that solution is that the Einstein frame metric is perfectly smooth, but the dilaton is not smooth. Okay, so the non-smoothness of the dilaton give rise to non-smoothness of the string frame metric. And the main challenge or main calculation is to quantify this non-smoothness. And a lot of effort in our paper goes into just quantifying this singularity. So A is the rotation parameter of the curve black hole. So what we have done is that we have replaced with A with IB. And then the dilaton of this Horowitz and black hole is of this type. So there is some function delta on the numerator. So delta is just some complicated function depending on charges and boost parameters and something of that type. But the numerator has this radial coordinate square minus b cosine square theta whole squared. So rho is the standard coordinate and A is IB. A is the standard rotation parameter. And this M0 and alpha, you don't have to worry so much. These are related to charges. Yeah, I don't need to explain more. What is this? Okay, so since the scaling argument of Sen requires that we take the large charge limit, it is best to explore the string frame metric in the large charge limit near the singular surface. In particular, you see there is a singularity here. When rho equal to b cosine theta, cosine theta equal to plus minus 1, so rho equal to b is a singular surface. So in order to analyze the solution near the singular surface, we introduced the following coordinates. So this was another crazy. Yeah, the dilaton remains weak all the time. So e to the minus phi. So this, so even if this diverges, the string loops do not become important. So that's why the scaling argument continues to work. Yeah. Okay. So this was another crazy, difficult part of the project. How to find the correct coordinate transformation so that we can analyze the solution near the singular surface. So the singular surface is rho equal to b, cosine theta equal to 1. And then, given my experience with the crazy metrics and coordinates and so on, I came up with these coordinate transformations. So you do these coordinate transformations. And after these coordinate transformation, this allows you to zoom in at the singular surface. So the reverse of these transformations are these. And now you look at it. So if you put r tilde equal to 0 in these equations, then rho becomes b. This term becomes 0, this term becomes 0, this becomes 0, rho becomes b. And when you put r tilde equal to 0, this becomes 1. Cosine theta becomes 1. So this term becomes 0, this term becomes 0, this becomes 0, this becomes 2b, and this becomes 1. So we can zoom in at r tilde equal to 0, which is same as zooming in at rho equal to b, cosine theta equal to 1. So now there are some details. So when you do these coordinate transformation, one has to worry about the ranges of these coordinates. So theta tilde, the way it is introduced here, has range from 0 to 2 pi, 0 to pi for all dimensions. And these coordinates have this important property which I explained, that when you put r tilde equal to 0, you zoom in at this singular surface. And the singular surface turns out to be a SD minus 4 sphere. Okay, so when you analyze the geometry carefully, what you find is that there is a 4-dimensional space which has some sort of singular part, and then there is a d minus 4 sphere which is perfectly smooth and big sphere. In fact, it scales with lambda square actually. So this part is smooth, and this is the part which is not smooth. And this is a solution universal in the sense that one can do the scaling argument, and one can show that it is independent, one can make it independent of n and w. So in the same spirit as Sen's 1995 paper, one can show that this space is singular but universal. Now on this big SD minus 4 sphere, r tilde is 0, and the 4-dimensional part of the space is of this type. So this solution is universal except for this large sphere, and this metric, as you can see, this is not a smooth metric, because if this factor was not there, then this will be a smooth metric, but because of this 4, this metric is not smooth. In fact, there is a curvature singularity at r tilde equal to 0. Okay, so this is the singularity. So the nature of the singularity is like this. So if we restrict ourselves to 4 dimensions, then the singular surfaces are only at rho equal to b, cosine theta equal to plus minus 1. So only at the poles there is a singularity, but otherwise the rotating black hole has become smooth. And when these two centers coalesce, then it becomes a small black hole. So this is the picture. Okay, so now given this geometry, we can compute the on-shell action. The on-shell action that contributes to the log of the partition function. And what one finds that this action is some dimension dependent constant times some factor which depends on the charge, and times this omega d minus 4, which comes from the sphere d minus 4 sphere. All the b dependence cancels out. The answer does not depend on the rotation parameter. If we write this m0 in terms of physical charges, then it so happens that all the d dependence also cancels out. So what you get is just some constant which you cannot fix anyway, times square root nw. And if this capital K is 4 pi, then it agrees with the microscopic index. So while we do not know how to compute this K at present, the d dependence of the macroscopic answer is consistent with the d dependence of the microscopic answer. And now there is some sort of universal understanding of this in all dimensions, because we are first of all computing the index, and we are computing the index in general dimensions. And what we are finding is that irrespective of what dimensions you work in, the on-shell action turns out to be square root n times w, where all the dimension dependence factors have cancelled out, and rotation dependent parameters have also cancelled out. No, because the scaling argument has gone in here, and there is a singularity at the pole. Near the singularity, higher derivative terms become important, and we do not know how they contribute. We do not know.
But do you know that the higher derivative terms will also have the same scaling?
Yeah, that we know. So from scaling, this is the sense scaling argument. Yeah. So just a comment. So the previous talk I gave in February, so Dabolkar's calculation is what we did in the next paper, and that I explained in the February talk. But we only did it for large black hole. We did not write anything about the small black hole, but okay. So I think this is a good time to end for questions, comments, and so on. So what we discussed is how to compute the supersymmetric index for small black holes on the gravity side. Since 1995 scaling argument can be used to show that the index must also scale in the same way as the entropy. It scales as square root NW with some numerical constant key C, which we cannot fix right now. All the contributions comes from the singular surface. Roughly speaking, the S, the area plus 2 pi ij, they cancel. And then one has to argue that there is some contribution from the singularities which we do not know how to compute, but we can estimate the contribution which scales as square root NW. And in doing this calculation, we also explain how the dimension independence works on the gravity side. Okay, so after this paper, I did several papers on this subject, and I gave a talk at IISc in February on higher derivative corrections. In another project, what we have done is that we have written the 5-dimensional saddle solutions in a Bina-Warner form. Actually, this solution, because it has these two singular sources, these two singular points, one can also write this solution into Bina-Warner form. And what we have done is something more complicated. We have written the 5-dimensional saddle solutions in Bina-Warner form, and we show that at the Bina-Warner centers, there is some sort of attractor mechanism that applies. In the most recent paper, which we wrote just a few months ago, in fact, in this month only, in the month of April only, before I came to Bangalore, I finished this paper. So in the most recent paper, we have done a similar analysis for a small black ring. And what we show is that the saddle solution is a 3-center Bina-Warner solution. It is not known what is the nature of attractor mechanism in 3-center. We are working on such a project also. Oh, something bad happened. Okay. So we are currently exploring a similar calculation, similar scaling analysis for a small black ring, where we want to show that the index scales as square root NW minus J. This has been argued by Dabolkar and Sen in 2005. This is a very difficult calculation. We are just starting to do this calculation. It is generally expected that all saddle solutions will be multi-center Bina-Warner solutions. However, the space of these solutions, especially with complex parameter, is too vast. It is not clear how to systematically explore this space. At present, it is not clear how to get organized in this search. Say, if you want to find the finite temperature index saddle solutions for finite area BPS black rings, this is a very interesting problem. Many people are thinking about this problem. And it is also, everybody agrees that this problem has a solution in the multi-center Bina-Warner solution, but the space is so complex and parameters are so many, it's not clear how to get organized. So several groups are thinking about this problem. We are also working on a similar project. So with this, I will stop, and yeah, thanks. So I'm happy to. Yeah. So the big development in this subject is now we know how to compute the index on the gravity side. And the hope is that this will help with supersymmetric localization at some point. And we might be able to compute the exact integers from a gravity calculation, hopefully, one day. And also what makes me quite happy is that these Bina-Warner solutions, you can't fix the C. So if I'm offline, then I can say more. So in Davolkar's calculation, what happens is that one of the moduli of this S1 becomes 0, the S size of the S1 becomes 0 size. Similar problem happens in when you compute the index in the higher derivative theory. What happens is that, so there are these centers, so the charges at these centers get modified, but the modification is quite drastic. So these centers get modified in a drastic way such that the final answer comes out to be square root NW with the correct factor. But because of this drastic change, it is not clear in what sense higher derivative corrections are playing a small role. So that's the reason we have not written anything in our paper about this higher derivative effects. Exactly. So there is no ADS2, and also, as I said earlier, there is a confusion whether small black holes have actually ADS2 or not. Because small black holes in n equal to 4 theories have 16 supersymmetries, but ADS2 times S2 with 16 supersymmetries is not possible. So there is a confusion with that. So it somehow bypasses all those confusions, but there are other confusions and subject remains unsettled. Hopefully it will become clear in few years. Yeah. Okay, so what I was saying, what I was saying is that what makes me quite happy is that these multi-center Bénard-Warner solutions, so two-center Bénard-Warner solutions are very well understood. They have an interpretation in the D1, D5 CFT, but three-center and more center Bénard-Warner solution have no interpretation. Like they have been known for 25 years, we still do not know how to interpret them. But this subject, like this index calculation, is giving us an interpretation for these multi-center Bénard-Warner solutions. So this gives me hope that eventually we will also understand what this Bénard-Warner solutions are. Okay, so with this I will stop. Thanks. Yeah. 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 No, so the only paper on higher derivatives is our paper so far, and before us there was the Chen-Murthy-Turiachi paper. Chen-Murthy-Turiachi paper was more of a conjecture that this will work. Our papers is the only calculation, detailed calculation right now. No, so it's exactly the same theory that Davolkar worked with. So n equal to 2 supergravity with pre-potentials, that theory. So actually this SENS paper I do not fully understand, but there is another I mentioned to you. So there is a similar paper by DeWitt and Zalk, Z-A-L-K, this person. So what they have done, they have proved some sort of non-renormalization theorem for BPS black hole entropy. The way they do this is that they consider like a bigger class of n equal to 2 supergravities, and they show that this bigger class does not contribute anything other than what was known before. So to me it looks like this calculation has some hope of adaptation, but this to this context, but this other calculation of Ashok I still do not know how. Also Ashok has this very important result that if instead of this very crazy supergravity, if you just work with the Gauss-Bonnet theory, then also the answer matches. But this Gauss-Bonnet theory we do not know how to use in the computation of index. Yeah, but I mean, in the ADS2, yeah, in ADS2 times S2 context, there is some explanation for this, because ADS2 times S2 is conformally flat, so Wild tensor is 0. So no matter what kind of Riemann square combinations you consider, you can convert them into Gauss-Bonnet. And there is some semi-intuitive explanation for why this Ashok's calculation works. But yeah, I mean, you cannot convert them. But what I'm saying is that whatever multiplies this W square is some function of scalars, and attractor mechanism fixes the values of those scalars. And if you can argue that this Weil square can be related to Gauss-Bonnet, then there is some sort of semi-heuristic argument one can give that why such a calculation works. But in the present context, it is not. I mean, we tried for some months. We still do not have a good answer. Yeah, Gauss-Bonnet we still do not know. We tried for some time. We do not know how to get organized with such a calculation. Yeah. So that's the reason I'm saying that calculation is not clear. But on the other hand, this Dewitt and Zalk non-renormalization theorem, that seems somehow is very complicated, but that seems much more manageable than this. Yeah, we hope to get the 4 pi intact. And, yeah. Okay, thank you very much. Yeah.